Morning, everybody. So in the previous class, we finished by introducing the Laplace transform. And we introduced the formula for the calculation of the Laplace transform. And what we said, if I have e to negative 1 minus j10 multiplied by t, and we have e to negative 10 minus j 100,000 or 1,000, 10,000 t, which one of these numbers are bigger? First one? Which part is going to affect the magnitude of this number? The real part. So this is what I want you to keep in mind. This part is what's going to affect the magnitude. Does that make sense? So this 1,000, this is an oscillation. It's an exponential term. This is an oscillation, a sinusoidal term, both of these. The 1,000 and the 10. What's going to determine the magnitude is the real part. E to negative 1 multiplied by t, e to negative 10 multiplied by t. This is going to be decaying much faster. Okay, so what we're going to be doing today, we're going to continue on the Laplace transform. We're going to be introducing the properties of Laplace transform. And then we're going to start the transfer function. Okay, let's do another example on the calculation of the Laplace transform using the definition. Now, practically, how many times we're going to use the definition of the Laplace transform to calculate it in this class? None. Hopefully none. Okay, so if you have a sinusoidal term that want to calculate or exponential term that we're going to calculate the Laplace for, the integration from 0 to infinity, e to negative j omega t, e to negative s multiplied by t dt, which is going to equal the integration from 0 to infinity, e to negative s minus j omega multiplied by t dt. What is this integration going to equal to? E to negative s minus j omega multiplied by t divided by s minus j omega. And we're going to integrate it from 0 to infinity. Agree, everybody? And then we substitute the limits of the integration. And since we have this minus sign, we just flip the limits. So this is going to equal to 1 over s minus j omega. And we're going to substitute the 0 first. And we substitute the 0. What is we're going to get with this exponential? We substitute t as 0. A 1. 1 minus e to negative s minus j omega multiplied by infinity. What is this integration going to equal to? Only when? When the real part of s has to be greater than 0. Is that clear, everybody? If the real part of s is greater than 0, it's going to be multiplied by a negative sign and infinity. This term is going to go to a 0. Again, this j omega does not affect the magnitude. It's just oscillation. Just the real part multiplied by infinity has to be negative infinity, so therefore the real part has to be greater than 0. Together, everybody? Okay. Let's look at the properties of the Laplace transform. What is the first property when we look at properties of these transforms? Anybody remembers? Linearity. Laplace transform is a linear transformation. What does that mean? Anybody remembers the definition of linearity?
Does it mean like one for one? Like what you put in, it's going to affect what you get?
What else?
Homogeneity and additivity.
Excellent, remembering that. What does that mean? If I have a function f of t that has a Laplace transform that is f of s, and I have another function g of t that has a Laplace transform g of s, then if I take these two functions and I take a multiplied by f of t plus b multiplied by g of t, what is the Laplace transform going to be?
A f of s plus b g of s.
Excellent. Is that clear? Additivity and homogeneity. Why is this important? Or why is it useful to know that it is linear transformation? What is it?
It makes it simpler to work out.
How?
It's consistent. You can tell what you're going to get on the other side. It's not like going to have variations.
What else? We can?
You can take out constant.
What else? Well, yes, good point. What else?
You can break down more complex ways.
Excellent, yes. I mean, the reason this is very useful, because if I have an expression that I want to find the Laplace transform for, what I can do, I can take it and break it into smaller parts, and then find the Laplace transform for each part, and then add them together. Make sense, everybody? Okay. Another property, and we'll look at the properties and we'll do examples, is the transition in time or delay in time. If I have a function f of t that has a Laplace transform f of s, then if I shift this function f of t minus a multiplied by u of t minus a, then this function is going to have a Laplace transform that is e to negative a multiplied by s f of s. And what that says, if I have a function that looks like this, this is f of t, and then I shifted this function to get f of t minus a multiplied by u of t minus a, and this is the a shift, then this is going to result in this exponent in the Laplace transform. Another property is the transition or translation in the frequency domain. Similar to the translation in the time domain, if I have f of t that has a Laplace transform that is f of s, then if I shift f of s minus a, is going to correspond to e to a multiplied by t f of t. Another property of the Laplace transform is differentiation. And what this property says, if I take the derivative of a function f of t then the Laplace transform of that derivative is going to equal to s multiplied by f of s minus f of 0. If I take the second derivative by t squared, it's going to be s squared f of s minus s f of 0 minus f prime of 0, the derivative at 0. Why is this property important, or how are we going to use this property? When did we use this property? From previous classes, when we solve differential equations. We take a differential equation, we turn it into algebraic equation using this property. Of course, this continues, but the most useful, or the most we will see, first and second derivative. Okay. Another property is the integration property. The Laplace transform of the integration from 0 to t f of tau d tau is equal to f of s divided by s. Now we notice here, when we integrate, what's going to happen to f of s? It's divided by s. When we differentiate, what's happening to f of s? Multiplied by s. So every time we see an s in the numerator, we know this is coming from where? A differentiator. Every time we see s in the denominator, where is this coming from? An integrator. And we'll be using that later on. Okay, another property is the final value theorem. And what the final value theorem says, if you want to know how the function behaves as t goes to infinity, f of t, you can find that by taking the limit as s goes to 0 of s multiplied by f of s. And another property that is very related is the initial value theorem. The limit as t goes to 0 of f of t is equal to the limit as s goes to infinity of s multiplied by f of s. Where do we use the final value theorem? What is it?
I said at the end.
After a long wait. Anybody can think of
To use it to do divergence or convergence to check.
what else? We're going to be using it when we look at the steady state error. Make sense? I mean, we want the steady state error. So if I have the error, the expression for the error function, I can find the steady state error by using the final value theorem. Okay. Now, since we wrote these, I'm going to write what is the precaution that we always have to write when we talk about the final value theorem and the initial value theorem. What is it?
The functions are continuous.
If the limit exists. Anybody's going to remember that?
Wasn't it in like signaling systems or something?
It's everywhere. I mean, it did not change since they introduced it. But always, when you see final value theorem, initial value theorem, the first thing is going to come to your mind, oh, I have to be careful when I use it. I can only use it if the limit exists. Okay. The other thing we notice about this expression for the final value theorem and the initial value theorem is the following. When I look in the time domain, the behavior of the function when t goes to infinity is determined by very small value of s. The behavior of the function when t goes to 0 is determined by very large value of s. So therefore, we can write that the behavior of f of t in the neighborhood of t equal to 0 is related to high frequency and similarly the behavior of f of t in the neighborhood of t goes to infinity is related to low frequency. Okay. Let's look at some examples and the application of the properties of the Laplace transform. So the first example, we're going to find the Laplace transform of cosine omega t. How can we use the properties of the Laplace transform to find the Fourier transform of cosine omega t without having to use the definition and only using what we already introduced in this class or what we've done in this class, today's class? Any ideas? When you have a cosine, what is the first thing that will come to mind? Beside the sign. The sign is not helping. We can write it as e to j omega t plus e to negative j omega t divided by 2. Everybody remembers this formula for the cosine? Yes? No? Yes? What is it for the sine?
Is there a minus in between the e?
What else? It is a minus.
2j.
Over 2j. Excellent. Okay. So how does this help us find the Laplace transform? And we've done, what was the first example we've done? We've done this, isn't it? We know the Laplace for this. And we know, what else we know? We know the transform is linear. So we can take these parts and add them together. So therefore, f of s is going to equal the Laplace of e to j omega t divided by 2 plus the Laplace of e to negative j omega t divided by 2. What is the Laplace of the first term? What is it? 1 over s minus j omega, and we have also the half. So we have 1/2 multiplied by 1 over s minus j omega, plus we have 1/2 multiplied by 1 over s plus j omega. Agree, everybody? Again, we've done this at the beginning of the class. 1 over s minus j omega. And if it is minus, it's going to be plus j omega. How do we simplify this? It's going to equal 1/2. And if you multiply these together, s minus j omega multiplied by s plus j omega, what is that going to give me?
Squared.
Good. Okay. And then we're going to have s plus j omega plus s minus j omega. And therefore, we're going to have 1/2 multiplied by 2s divided by s squared plus omega squared, which is going to equal to s over s squared plus omega squared. So therefore, the Laplace transform for the cosine is s over s squared plus omega squared. Anybody want to guess what the region of convergence is going to be? Well, I mean, not guess as in guess. I mean, educated guess. At least one person knows the answer.
You are the one person.
Okay, I'll take that answer. I mean, this is linear. We calculated for the first term that the region of convergence was the real of s greater than 0. The second term is going to be real of s greater than 0. What is the region of convergence then? Real of s greater than 0. Make sense? I mean, we're adding the two terms together. The region of convergence is going to be the intersection of this and this. But both of these have a region of convergence that is the real of s greater than 0. Make sense? Everybody? Convinced? Okay. Let's do another example. F of t equal to sine omega t. How do we find the Laplace transform of the sine? Based on what we've done.
We turn the sign into u to j omega t.
We can do that, but we don't want to repeat anything we've done in this class.
You take the answer and flip a negative sign somewhere.
Which one?
The s over s squared plus omega squared.
This one?
Is it going to be similar to that?
Related, but how is it related? Well, we know that the sine omega t is equal to negative 1 over omega, the derivative of the cosine omega multiplied by t. Agree? The sine is the derivative of a cosine multiplied by negative 1 over omega. So therefore, we can use this to calculate the Laplace of sine omega t. Is going to equal negative 1 over w, the Laplace of d by dt of the cosine of omega t. And this is going to equal to negative 1 over w. What is the property that we're going to use to calculate this Laplace? Differentiation, yes, the differentiation property. This is going to equal to s multiplied by the Laplace of the cosine omega t minus cosine of 0. again, let me go back to the differentiation property. S multiplied by f of s minus f of 0. S multiplied by f of s minus f of 0. Okay, so what is this going to equal to? Negative 1 over w multiplied by, we have an s and we have s from before, it's going to be s squared over s squared plus w squared minus 1, which is equal to negative 1 over w multiplied by s squared over s squared plus w squared minus s squared plus w squared over s squared plus w squared, which is going to equal to negative 1 over w. And what's going to survive in the numerator is negative w squared divided by s squared plus w squared. And therefore, this is going to equal to positive w over s squared plus w squared. Everybody agrees? Is it clear? Is it as clear as driving to school this morning? Okay, just keep in mind, when we have, this is f of 0, how is this different than this? Anybody knows what I'm asking? This is f of s, this is f of 0. What is this? In the time domain. This is from the time domain. It's small letter. So this is the time domain, value at 0. And therefore, when we substitute the function in the time domain at 0. Make sense, everybody? And we're subtracting a 1. So we wrote it as s squared plus omega squared over s squared plus omega squared. What is this equal to? A 1. Okay. Okay, let's do another example. Given f of t equal cosine omega t, and it has a Laplace transform that is s divided by s squared plus w squared. Find the value of f of t as t goes to 0 and as t goes to infinity. What property are we going to be using to calculate when t goes to 0 and t goes to infinity? The initial and the value theorem, yes. So using the initial value theorem, f of 0 or f of t is going to equal to the limit as s goes to infinity of s multiplied by f of s. Together? Again, from the property. What is this going to equal to? The limit as s goes to infinity. We had s multiplied by s. We're going to have s squared over s squared plus w squared. What is this limit going to equal to? As s goes to infinity, when s goes to infinity, this w squared becomes very small compared to s. So it's going to be s squared over s squared, which is equal to 1. Or if we substitute s infinity over infinity, we use L'Hopital's rule to derive. We're going to get 2s over 2s, 2 over 2, which is going to equal to a 1. Is this correct? How? Excellent. Because we know cosine of 0 is equal to a 1. So this checks. Then we're going to find the final value. Use the final value theorem. So f of t, the limit as t goes to infinity is going to equal the limit as s goes to 0 of s multiplied by f of s, which is going to equal the limit of s squared over s squared plus w squared. What is this limit equal to? 0. Together? Everybody? Now one thing, please, people are going to make this mistake. When they use the final value or initial value, they're going to forget to multiply by this s. Anybody's going to forget to multiply by this s? Let's highlight it. I'm afraid now, because I highlight it, we're not going to see it. What color we highlight? Purple? That's extreme. Then you'll have an excuse. When you print it, you say, oh, it was, I could not see the S from. Does anybody print the handouts? Yes, but if you ever print them, the problem with the colors is like you might not be able to see on top of each other unless you print color. Is this correct?
Yes.
No?
It's the limit is because I guess the limit doesn't exist.
Okay, we have somebody saying yes, somebody saying no. Any votes for the no? Votes for the yes? Even the no is a minority, it won.
I don't know.
This is not correct. Why is it not correct? Because the cosine is not defined at infinity. Make sense? The cosine is oscillating at infinity does not have a value. Everybody knows that? And therefore, when we introduce this theorem, what did we say? If the limit exists. And what did I tell you? Whenever you apply this, you're going to apply it, and in the back of your mind, you're going to remember, oh, there's a trick to it. Oh, there's a trick to it. Do you not apply it blindly and then, oh, I got result, everything added up. Here, it looks 0. What's wrong with the 0 here? After you get this result, you're going to say, oh, but does the function have a limit or not? If it does not, then this value is not valid. Is that clear? Everybody? Everybody's going to remember that? Okay. What I want you to remember is that you only apply these if the limit exists. If the limit does not exist, then the result is not valid. Therefore, we cannot apply the final value theorem. And here's an exclamation mark. Okay. Let's do another example. And we'll see this later on in more details, but for the time being, let's say that we have a potentiometer that we're connecting to an op-amp, to an amplifier, and we're connecting that to a motor, and we're connecting the shaft of the motor to a load, and then the shaft is connected to another potentiometer. And then we're going to take the value of the potentiometer and feed it back to the op-amp. What does this look like?
A circuit.
That does what? What are we trying to do? What is that?
Is it like the satellite example?
Yes, it is like this.
Okay.
It's a position control system. Make sense? I change the potentiometer here. The motor is going to spin. This is going to change. The motor is going to rotate. The volt is going to change till I have a 0 volt. The motor is going to keep running. Make sense? Okay, so in few classes we're going to learn, we're going to be able to take this system and represent it with a block diagram that's going to look something like this. This is our motor, and this is our feedback loop, and this is going to be our input R. This is going to be our output C, and then we're going to define an error signal that is here. Why is this the error signal? Anybody?
It's the difference between the output and the
Excellent, yes. It's the input minus the output. R minus C. If I have an input, I have an output. The input minus the output is the error. So this signal here gives me that, R minus C. Okay. So let's say for this system, C of S is equal to A divided by S squared plus 2S plus A. And the transfer function E of S divided by R of S is equal to S squared plus 2S divided by S squared plus 2S plus A. And let's assume that the input is a unit step. When I find the steady state error. Make sense? What does a unit step at the input mean?
starts at 0 and
Like I came to this potentiometer, has a setting from 0 to 10, I put it at 1. Make sense? What can we use to calculate the steady state error?
Final value theorem.
Thank you. Final value theorem. The steady state error, E steady state, is going to equal the limit as t goes to infinity of E of t. And this is going to equal the limit as s goes to 0 of s multiplied by E of s. This is the formula, isn't it? And what is this going to equal to? Can anybody tell me? Or read it for me? What is it?
S cubed plus 2s squared.
Well, s multiplied by s squared plus 2s divided by s squared plus 2s plus a. Is this correct? What is it missing? Is it missing anything?
Would you have to pull out R of S because that's just E of S?
Excellent. Yes, that's correct. It's missing R of S. I mean, this expression for E of S over R of S equal to this. Therefore, what is E of S is going to equal this multiplied by R of S. What is R of S? Since it's a unit step, who knows what the Laplace transform of a unit step? No. Step
1 over S?
1 over S. Excellent. Why did I emphasize it like this? Because some people are going to forget to multiply this. Okay. What is this limit going to equal to? Zero. And therefore, we have no steady state error. Make sense? Everybody? Now we will see later on when we look at the steady state error, we have to do one more thing in order before we calculate the steady state error, which is make sure the system is stable. And we'll see what that means later. Sounds good, everybody? Okay. Any questions? Okay. The next thing we're going to look at is transfer functions. Now that we reviewed the properties of the Laplace transform, let's look at how we can get a transfer function. If we have a system that is described using an nth order differential equation, what is ODE?
Ordinary differential equation?
Does everybody know it? Okay. So let's have a system that is described by an nth order differential equation. an minus 1 dn minus 1x divided by dt n minus 1 is 0 multiplied by x equal to bm dm r by dt m all the way to be 0 multiplied by r. If I want to take this differential equation and generate a transfer function, what do we have to do? How do we get a transfer function from the differential equation? We take the Laplace transform and we take the output, put it together, the input together, and then take the ratio. So what we're going to do is we're going to take Laplace transform what is the Laplace of the nth derivative of x? Okay, we did not say that. But the first derivative, we got s to d1. Second derivative, s to the 2. Third derivative, what is it going to be? Nth derivative, s to the n. So if I take for the nth derivative of x, I'm going to get s to the n plus a n minus 1. What am I going to have here? S to the n minus 1 all the way to a0. And what do I have this multiplied by? X of s. Together? And what is this going to equal to? We're going to do the same thing on the other side. We're going to get bm s to the m all the way to b0 multiplied by r of s. Anybody not happy with this? Anybody happy with this? What are we missing here?
Blank spot.
What is it?
There's a blank spot.
Yeah. Why do we have that blank spot? Because we have terms that we skipped, isn't it? I mean, if you look at when we take, there is f of 0, sf of 0, f prime of 0. You see it? So what we've done is that I took the first term, and then all the other terms, I'm going to just put them here. Make sense? What am I going to call these? Initial conditions. All these are coming from initial conditions. F of 0, f of 0, f prime of 0, f second prime of 0, triple prime of 0. All these are initial conditions. I'm going to take them all and just put them in that box there. Okay. So therefore, I can write this as x of s equal to bm s to the m plus bm minus 1 s to the m minus 1 all the way to b0 divided by s to the n plus an minus 1 s to the n minus 1 all the way to a0 multiplied by r of s plus initial conditions. Is this correct? Initial conditions divided by all this.
Do you subtract the initial condition?
No, I didn't. I had this. I moved the initial conditions to the other side, and I divided by this term here. Make sense? Probably I should write this as minus sign here, because I moved it to the other side.
Don't you divide
Oh.
everything by,
Go ahead.
don't you divide everything by the...
Yes, yes, that's what I'm saying. This should be also divided by s to the n plus a0. Make sense, everybody? Okay. Now what we're going to do, I'm going to set all these initial, well, I can write this as x of s. I'm going to take this expression that I have here, and I'm going to call it g of s multiplied by r of s. And all these terms, the initial conditions, I'm going to call them initial conditions of s. Good? So all these expressions, I'm just going to call them the initial conditions. This expression, I'm going to call it g of s. Then what I'm going to do I'm going to set the initial conditions to 0. Therefore, I'm going to have x of s equal g of s multiplied by r of s. What do we call this g of s? What do we call g of s? The transfer function. Everybody with me? Anybody confused? Yes, no? Not yet? Okay. So therefore, what is the transfer function? It is the ratio between the Laplace transform of output to Laplace transform of input when all the initial conditions are set to 0. And this is what the transfer function is. Does that make sense, everybody? So if I have a differential equation that relates the output and the input, first thing I'm going to do, I'm going to set the initial conditions to 0. So when I use the differentiation property, I'm going to ignore all the terms that are coming from initial conditions. I'm going to assume the system, all f of zeros, all f prime of zeros, or f double prime of zeros are equal to a 0. If this is 0, then what is the f by dt going to equal to? S f of s. If these are zeros, what is the second derivative? S squared multiplied by f of s. What is the third derivative going to equal to? S squared multiplied by f of s. Make sense? All these initial conditions are set to 0 by design. We set them to 0. And then I take the ratio between the output to the input. That ratio is going to equal to the transfer function. Make sense? Everybody? Okay. Let's do an example and see how that applies. So again, we have a system. We have an input, R of s. This is G of s. This is the output, X of s. X of s is equal to, or G of s is equal to the ratio of the output, X of s divided by R of s. Okay. And before we do an example, just one more definition. When we have G of s, this is a polynomial n of s divided by a polynomial d of s. D of s, we refer to it as the characteristics polynomial. The denominator of the transfer function is the characteristic polynomial. Does anybody want to guess why we call it the characteristics polynomial?
Characterizes
The system, yes, because it's going to give you information about the character of that system. Therefore, characteristics polynomial. Okay. The poles of the system What are the poles of the system? What is it?
Not zero.
Excellent. Are the roots of the D of S. The zeros of the system are the roots of N of S. Make sense? Again, we're going to be using this throughout the semester, so you will know it by heart. Okay. So let's take an example. I want to find the transfer function of a system that is described by dc by dt plus 2c equal to r of t. And these are function of time, c of t, c of t. Where is this differential equation coming from? Where is it going to come from? From the system that we're trying to model. Make sense? Remember on the things that we're going to be covering this semester, we're going to modeling system. So I'm going to come to a system. It has an input R, it has an output C. I'm going to try to relate them together. And then I came up with this differential equation that described how they are interacting. Now I want the transfer function. How do I get the transfer function? I take the Laplace, yes. So I'm going to take Laplace transform. What is the Laplace of the first derivative? S multiplied by C. And this is a small letter c. This is going to be capital letter because it's in the Laplace. And that's the convention. I forgot probably to mention this. In the time domain, we're going to use the function in small letter. In the Laplace, we're going to use capital letter. Okay, so s multiplied by c plus 2 multiplied by c equal to r. What do we do next? We take the ratio of the output over the input. The transfer function g of s is going to equal c over r. And what is c over r going to equal to? 1 over s plus 2. Make sense? We take a c, common factor, and then we divide by r. It's going to be 1 over s plus 2. Okay. Is that clear, everybody? Transfer function? Now, if you look at a linear time invariant system, what are the different ways we can model that system or represent that system? So we have a transfer function, isn't it? This is one way we can represent the system. What are other ways we can represent the system?
Like a block diagram.
Okay, what else? I mean, keep iterating till I get the answer I'm looking for. What is it? So if I tell you like, oh, I have this system that I really want you to analyze it, help me with it. Okay, can you go analyze it? Tell me, oh, go analyze it. I mean, give me, what are you going to say? Give me,
Graph.
okay, what else? You can say, give me transfer function. I'll tell you, oh, and I'm not there yet. What else would you be able to give me?
Give me the input and the output.
How are they related using that? Anybody was going to ever say impulse response? Nobody? I'm glad we waited then. Okay, another way we can represent the system is using the impulse response of the system. Anybody remembers the impulse response? What do we refer to the impulse response? What letter of the alphabet we use to represent the impulse response?
Delta.
No, impulse is delta. Impulse response. H of t. H?
That's 2 letters.
Huh? Sorry?
That's 2 letters.
Oh, H. of t is just comes with the letter. Okay. So again, this is on the side, but I want you to know this. If I analyze a system in the time domain, I have a block here that I do not know anything about it. What I can do, I can come here and apply a delta function. What do I get at the output?
The response to the delta function.
Which is
The impulse response.
the impulse response. What I'm going to get here is h of t. Is that clear? Makes sense, everybody? Now what happens if I come and I apply another input, x of t? How do I find the output? Anybody does not know the answer?
Just get the response of that input.
How do I get it? So if I gave you h of t, and I gave you, okay, now I have an input that is x of t, what is the output?
X of t times h of t.
I mean, that's a good guess. That is wrong. Anybody? It is.
T divided by delta T.
A good guess. That is even more wrong. It is the convolution. If I apply another function, once I know h of t, if I apply a function, another input, x of t, what is the output going to equal to? X of t convolved with h of t. Does anybody know this? Yes? No?
Wouldn't say no, but I remember it.
Yeah, I mean, we've seen it, I'm sure.
Yeah.
But what I want you this time to do is I want you to know it like you know what is one thing you will never forget.
My neighbor.
What else? I do want you to know it like your name. Please try to remember this. This is very important. If I have a system, I apply the delta, I got h of t. This is the impulse response. If I come and I apply any other input, I can find that output by convolving that input with h of t. Okay. Now, why is that? How is that related to our discussion? If I come and do this in the Laplace domain, what is the Laplace of the delta function?
Dig into that.
The Laplace transform of a delta.
Dig
So-
into that.
What is it?
Over at
1. It is just a 1. A 1. So the Laplace, this delta in the S domain is going to equal to a 1. Together? So if I come in the Laplace domain, I apply a delta in the Laplace domain, that is equal, the output is going to equal to h of S. And therefore, if I analyze the system in the Laplace domain, this is h of t, this is h of s, the output is going to be x of s multiplied by h of s. Does that make sense? The convolution in the time domain, what does it become in the frequency domain? Multiplication. Now, if I look at this, let me call this y of t equal to this, y of s equal to this. H of s is equal to the output y of s divided by the input r of s. But if r of t, which is the input, if r of t is equal to a delta of t, then r of s is going to equal to a 1. And therefore, h of s is going to equal to y of s. Does that make sense? So what that says is the following. When I calculate this g of s, if I take the inverse of g of s, inverse Laplace, what is that going to give me? G of t. What is that g of t? Is the impulse response of that system. Together? G of t is the impulse response of that system. If I take h of t, the impulse response, and if I take the Laplace transform of it, it's going to give me the transfer function, h of s. H of s is y of s over the input. Y of s over s. This is the transfer function, isn't it? What is the inverse of h of s? H of t, which is the impulse response. Together? So if I have a system, if I analyze it in the time domain, I'm going to use h of t. If I want to calculate the output, I'm going to do the convolution. If I analyze it in the frequency domain, I'm going to take the Laplace of h of t, is going to give me h of s. To calculate the output, I multiply the input with h of s to get the output. Convolution in the time domain is multiplication in the frequency domain. Is that clear, everybody? Okay. Okay, so in order to be able to calculate the output of the system, when we are given the transfer function, we're going to need another tool that will help us take the transfer function and break it into smaller pieces so we can easily find the inverse Laplace of it. What is that tool? The partial fraction expansion tool. What is the idea behind the partial fraction expansion? I want to be able to take a rational function and break it down into simpler terms, such that each of these terms has a known Laplace transform. Together? Is it clear what we're doing? So we're doing transfer function. Now I want to be able to calculate the inverse of a system that has a transfer function. But if I look at transfer function and it's a fourth order transfer function, how am I going to calculate the inverse Laplace of it? Make sense? So if I tell you calculate the inverse Laplace of s to the 4 plus 3s squared plus 2s plus 1 over 3s squared plus 1. How do I calculate the inverse of this expression? Can we? How? Partial fraction expansion. Okay. So again, the idea, I'm going to be able to take n of s, a polynomial, over a polynomial that might look something like this. So this is what we wrote here. And I want to be able to break it so it look something like this. And what are these P1, P2, P3, etc.? The roots of D of S. Make sense? Okay. Now, before we do the partial fraction expansion, when we look at any transfer function, we're going to have one of three situations. The first one is that the degree of the numerator is going to be greater than the degree of the denominator. Make sense? Numerator greater than denominator. We can have the degree of the numerator equal to the degree of denominator. And what is the third case?
The numerator is less than.
Why did I write the D small letter? What is it?
For the time.
No, for no good reason.
Oh.
I don't want to be studying. It's like, oh yeah, but there must be something. Why would you write this D, small letter, this D? Must be a trick there. I did not. Okay. So what do we call the transfer function that has a degree of the numerator greater than the degree of the denominator? We call it improper. What do we call the degree of the numerator equal the degree of the denominator? Proper. What do we call when the degree is less than the numerator?
Bottom heavy.
What is it?
Bottom heavy.
Strictly proper. Good? So we can have any of these cases. What is an example of a system where the degree of the numerator greater than the degree of the denominator? What is the simplest example?
And just make
X
one up.
squared over X.
There's no over x. It's a transfer function. Numerator and denominator has to be a function of s.
S squared over
S squared over,
S.
which is equal to what?
S.
S. F of s equal to s. The degree of the numerator is greater than the degree of the denominator. What is the f of t of this? How does it?
One.
No. Okay, what is an example of a proper one? I mean, people don't seem interested in knowing, so I won't know. This is the derivative of a delta of t. A delta gives me a 1. The differentiation property gonna give me an s. What is an example of a proper transfer function?
S plus 1 over S.
Very good. We'll take that. F of s equal to s plus 1 over, let's make it s plus 2. Now when I have the degree of the numerator equal to the degree of the denominator, what I can do, I can divide them. How do we divide these polynomials? s plus 1 divided by s plus 2. What is s plus 1 divided by s plus 2? S divided by s is equal to what? A 1. And 1 multiplied by s plus 2, I'm going to get s plus 2. We reverse the signs, we get a negative 1. Make sense? This becomes negative, negative. This will cancel. Negative 2 plus 1 is negative 1. So therefore, what is s plus 1 equal to? A 1 plus negative 1 over s plus 2. Agree? Everybody? Okay. And the third case, and we'll stop here, is when we have f of s, the degree of the polynomial of the numerator is less than that of the denominator. Okay, so we're going to assume when we do partial fraction expansion, we have a strictly proper transfer functions. If not, if it is improper, if it is proper, we can divide to get a strictly proper. Okay, I will stop here.